Hello and welcome to our first class on coordination compounds. This is SS Tripathi welcoming you for this program. This will be a live streaming program. Students can watch it even later than today. Today is in India, it is morning 5 a.m. 27th Friday, September. You guys are able to hear me?
Yes.
Okay. Are you able to hear me?
Yes, sir.
I am able to hear you. Hello and welcome. Once again, it's morning 5 a.m. Let me share my screen so that we shall start our program. Can you see my screen? Can you see my screen?
Yes, sir.
Yes,
Okay. Since it is a YouTube live program, we will be sticking to the time. It will be a 1 hour program, mostly, maybe 10 minutes more, max. We shall be looking to various aspects of coordination compounds, also called complex compounds. Why it is called coordination, why it is called complex, I'll tell you. You must have come across with several complex compounds like potassium perocyanide. Like potassium dicyanide or argentine. All these types of complexes like CuNH3 whole 4, SO4, and so on and so forth. And sometimes it is neutral. There is nothing before or after the square bracket. The first example where the complex is an ion, which is a negative ion, ferrocyanide ion is the complex ion. And this compound is the coordination compound, but the ion, which is the complex ion, is ferrocyanide ion, and it is anion. And in this case too, this is an anion. But here, the complex ion is a cation. And there is no ion here. This is non-ionic, neutral. So in a coordination compound, you have a complex ion or a neutral complex molecule. So complex, inorganic complex is made up of a metal ion or sometimes metal atom plus ligands. These two are put inside a square bracket and it has got a net charge, say n plus or n minus, or it may be 0. So ligands are donors, electron donors, not a rupee donor or dollar donor. I am transacting here in dollars now. Presently, I am at US, as you know. And therefore, these ligands act as Lewis bases. And metal ion or atom acts as electron acceptors. And hence, they act as Lewis acids. You must have studied while Lewis concept of acid and base was discussed. You know, for example, BF3 reacts with ammonia. Ammonia is a Lewis base and BF3 has a vacant p orbital, is a Lewis acid, and there is a donation of a lone pair, you have a dative bond. So what happens? I'm writing ammonia in the left side and BF3. Usually the kids, they put a arrow mark, but you are no kid. You write a donor will have a formal positive charge and the acceptor will have a formal negative charge. So usually a, a lay student or a kid below class 10, we used to show a arrow mark for the dative bond. This is called coordinate covalent bond. This is sharing of electron pair, but contributed solely by one atom, and that is the ligand atom, which contains the donor atom here. The donor atom is nitrogen, ammonia is the Lewis base, BF3 is the Lewis acid, and there is a coordinate covalent bond or a dative bond. This justifies why the compound is called coordinate compound, coordination compounds, because there are all coordinate covalent bonds. Now, for example, we analyze this FeCN whole 6. This is an anionic complex ion with 4 minus. Since cyanide ion has a valency of -1, has a charge of -1, there are 6 cyanide ions, the total negative charge is +6. And the net charge of the complex ion is -4. So iron is in the +2 oxidation state. So iron is in the +2 oxidation state at the center. And if you draw an octahedron, iron sitting at the center of the octahedron, and these ligands, these are called ligands, they're at the 6 corners of an octahedron. So these bonds are really dative bonds. I treat you as a lay student, which you are not. You are a very, all of you are intelligent students. So these are covalent bonds. And this entity is called, it's getting, the whole entity is called the complex ion. So inside the bracket, you have the central metal ion. This is the central. You can use your pen and paper because I will be doing very fast. I will be taking off first gear, then second gear, third gear, and then top, fourth and fifth gear I will take. So this is the central metal ion. You can call metal. It may be an ion or maybe sometimes having no charge, zero charge. So central metal atom sometimes we can call, and we shall assign the oxidation state. So iron is in the +2 state, ferrous ion, it is being coordinated by 6 ligands. These are ligands which have a pair of electron, at least one pair of electron to donate. They have donated, and these are all covalent bonds. And the shape of this ion is octahedral because it is covalent. Covalent bonds, as you know, are directional. Therefore, the covalent substances, may it be an ion, may it be a neutral molecule, has a fixed shape. So, ferrocyanide ion is a covalent ion. The iron is in the +2 state, and there are 6 cyanide ions which have linked, bonded to the central metal ion by covalent bond, and that is coordinate covalent bond. That is why these compounds are called coordination compounds. And this Lewis acid, Lewis base, that salt, as we sometimes call, is a complex salt. That is why it is also called complex ion. But complex word is little misleading. Complex word is little misleading, so I will refrain myself from using the complex word very often, because complex has many wide versatile application. So it will be better called coordination compounds, and sometimes, yes, we call complex compounds. Now let us proceed. So we know that a complex, inorganic complex, has two parts. One is the central metal, as I have already written, or metal ion or atom. Whatever I write down here, you must write down in your copy, because we are going in a very, very long journey. The intricate details of molecular orbital theory, valence bond theory, crystal field theory, stability of complexes, Color properties, and whatnot, central metal atom or ion, and ligands. Now, let us try to distinguish between the double salts, because when Werner prepared for the first time this very unique type of compounds, which he named as coordination compounds, it was previously called addition compound. Like we prepare a double salt by adding two salts and crystallizing, for example, kernelite, KCl, MgCl2, and 6 water. Now, you add KCl and magnesium chloride in equimolar proportion in water, and crystallize it, you get a double salt. When you put it in water, the identity is lost. It was giving rise to the same ions. So the double salt loses its absolute identity as it produces the same ions as the individual salts from which the double salts are prepared. For example, you have another example, potassium, potassium sulfate, aluminum sulfate, the alum that we often use in our villages after saving. It is a very good coagulant. If you have studied about coagulation in surface chemistry, if you have not done, we'll be doing that. Alum, this is a double salt. It has wonderful property, but it loses its identity. It produces K plus, aluminum ion, sulfate ion. I am not balancing. Same. But this kind of addition compound, what we call now coordination compounds, they are unique. They do not produce, once they are prepared, they do not produce the same ions. For example, you take ferrous cyanide and add excess of potassium cyanide. We write like this: FeCN whole 2 dot 4 KCN, but actual formula is not this. That was the big surprise to Werner, who propounded this coordination compounds. It was K4 FeCN6. This square bracket is given as an honor to the unique ion called the complex ion. And when you put it in water, they do not produce ferrous ion. Yes, potassium ion is produced, that is the counter ion, but instead a very bulky elephant-like ion, negative ion, ferrocyanide ion is formed. Does not produce cyanide ion, does not produce ferrous ion. But since you are very good students, later on, when we study ionic equilibrium, you will find the dissociation is there, but that is little. There is a dissociation constant, the opposite of the formation constant. So that is there. But for the beginner, we will presume that there is no ferrous ion, no cyanide, almost gone, as we used to solve problems in ionic equilibrium, assuming that since the equilibrium constant is of the order of 10 to the power plus 10 plus 15, then we presume that everything goes totally to the product side. But since there will be ionic equilibrium, there will be some infinitesimal small quantity of ferrous ion, cyanide ions will be there in equilibrium with the elephant ferrocyanide ion. But 99.9999% of ferrous ion and cyanide ion have been complexed, have been bonded by covalent bond, and that is coordinate covalent bond or additive bond. Is it going well, guys?
Yes,
And
sir.
uh, those who are watching, yes, uh, many guys are watching. Even in this early morning, I congratulate those who are watching in the early morning. In this is afternoon. I'm staying here in the west part of US, San Diego of the California state. This is in my watch. It tells it is 4:48, and in your watches it is 5:18 a.m. in the early morning. So I am really excited to find many guys, and I'm sure many guys will watch later. Undoubtedly, we'll be making this program little more in depth, so that only those who are aspirants to learn more things, they will be enjoying with me. About we'll be having about 10 classes. This is the first class. Okay. So distinguishing between the double salts, which lose their intensity, their identity by putting in aqueous solution, but complex. They are also addition compounds. They have been formed by adding two compounds. But once they are formed, the individual substances lose their identity. New complex ion is formed, which have unique properties that we shall study. Now, as I have told you that Werner was the first person who developed the theory of coordination compounds. So let us study. It appears in the exam. So we'll be studying in a very uh, simplistic way of without wasting much time. This is the primitive theory, coordination, Werner's theory of coordination compounds. is based on three studies. One study is chemical analysis. Usually reaction with excess silver nitrate. Conductivity measurement, because the ions in the aqueous solution conduct electricity and we can find conductivity, molar conductivity, as you have studied in electrochemistry, conductivity of solutions. And see the isomer analysis. He prepared, in fact, he was surprised. He thought it will be another kind of double salt. But once he found totally different properties, he was astonished. Just like Eureka in physics parlance. He was surprised. No, my new compound has completely different color, different magnetic properties. So what has happened? He prepared, let me write down complexes of cobalt 3 plus, platinum 2 plus, and platinum 4 plus, with the only ligand available was ammonia. With ammonia, I'm giving you the first set of 5 cobalt 3 plus complexes with ammonia. The first compound was cobalt chloride dot 6 ammonia. He got a different color. I will tell you the color. It is better that I should tell you the color now instead of. Yes, I will tell you the color in some time. And another compound, COCl3.5 ammonia. Another compound, COCl3.4 ammonia. Same cobalt chloride, but different proportion of ammonia. Cobalt chloride with 3 ammonia. And in the third category, 3A and 3B. And 4 cobalt chloride, 3 ammonia. And later on, he found the actual formula of the complex is CONH3 whole 6 Cl3. Tell me how many ions it will produce. Number of ions produced. Total number of ions produced. Moles of AgCl precipitated with excess AgNO3. What you would have got? I will tell you the color later. I will refer to the original file that I will give you. An interesting, a beautiful file with a lot of extra data I have prepared for you. I'll give you. But after we explain, after we understand and write down the minimum requirement in our copies. Now, how many ions are produced? Yes,
I
Udit.
think C, A and B are the same.
It's the four.
How many ions are produced? It
The
is,
four.
yes. Why? Because the elephant is one ion. The elephant number of total number of ions, number of moles of AgCl precipitated with excess silver nitrate. So tell me, this is 4. Why? This, if you ionize it in aqueous solution, this, no, I will write it later. This will give you the big, which have been coordinate covalent bonds with cobalt 3 plus with 6 ammonia, that is one ion, only one ion, very bulky, and 3 chloride ions. So total number of ions is 4. And how many moles of silver chloride will be precipitated from 1 mole of the complex molecule from the 1 mole of the complex molecule by adding excess of silver nitrate? Yes, tell me, Amlan.
Three.
Precisely 3,
3.
because the chloride ions are all outside the coordination sphere. Let me tell you one thing which is important for your examination. This bracket, this bracket, this is called the coordination sphere, that contains the central metal atom or ion coordinated by or bonded with the ligands. Coordination sphere, or sometimes called coordination entity, that contains the central metal atom plus ligands, written inside a square bracket, that space, that is called the coordination sphere. So we were, yes, since there are 3 chloride ions outside the coordination sphere, they are free ions, because the bonding between the complex ion and the counter ion, these are counter ions. Let me tell you, there are 2 types of bonds. Within the complex, it is covalent bond, and that to coordinate covalent. And between these between these two, potassium ion and ferrocyanide ion, it is ionic bond. And within the coordination sphere, all bonds are covalent, and that to coordinate covalent. So there are 2 types of bonds here between the if at all there is a counter ion. If the complex is neutral, there is no counter ion, there is no ionic bond at all. There will be all covalent bonds, right? Now, he prepared with 5 moles of ammonia, a compound whose formula later on he found that 1 chlorine as chloride ion is bonded to cobalt 3 plus with covalent bond, and 2 chloride ions are swimming like fish outside the coordination sphere. Let me, what is the total number of ions and how many maximum moles of silver chloride precipitated from 1 mole of such a complex? Yes, you can write
3
down.
and
Three
3
and
respectively.
three and two.
Many guys are watching. Uh, Ajit, Ajit Sihag, welcome. Funny shots, PW funny shots, welcome. Anil sir, you are omnipresent. You are omnipresent, Anil sir. Acha, she is from Barampura. Anyway, now definitely you have answered correctly, because the big ion is 1 and that the 2 loose ions swimming 2 chloride ions, so 2 plus 1, 3. And how many moles of silver chloride precipitated is only because of the 2 chloride ions. That will, this which is inside the coordination sphere bonded with a covalent bond will not budge an inch. It will be completely attached, linked to the central metal ion, will not go away from the coordination sphere, will not give a precipitate. He was really astonished. Same COCl3, but 1 mole of this complex using 5 moles of ammonia is not giving 3 moles of silver chloride. It is giving only 2 maximum moles of silver chloride by adding bucket full of silver nitrate solution. Means excess. And now, the most interesting part, he got two different colored complexes with 4 ammonia. It was a NH3 whole 4 Cl2, and outside there will be Cl2. One is cis, the other one is trans. Their colors were different. Tell me, each of them will produce how many total number of ions?
There's such a CL about it.
Yeah. Only one Cl. I'm so sorry. Thanks, Udit. So only one chloride ion will remain outside the coordination sphere, and two chloride ions will remain inside the coordination sphere, which will not be precipitated. So tell me, each of them will have maximum number of ions will be two, one big ion and one this chloride ion, and silver chloride, the number of moles of silver chloride is only 1 mole. But this has a different color, this has a different color. I will tell you the color in a bit. And finally, there was no ion at all. This is CO, NH3 whole 3, Cl3, nothing outside the coordination sphere. So 0, 0. No silver chloride was precipitated by adding bucket full of silver nitrate solution. No ion. This was corroborated by the conductivity. The maximum conductivity was found for the first, and minimum conductivity was found for this, and no conductivity was found for this complex. No conductivity was found for the complex with 3 moles of ammonia. That gave him this theory that he told in his time that concept, that terminologies have been obsolete. But you have to write in your examination. Werner suggested from these studies two types of valency for the complex. For the complex ion or complex molecule. If it is a neutral complex, like the third, like the fourth one, it is a complex molecule. One of them was the primary valency. It was the number of electrons lost by the central metal atom. Nowadays, it is called the oxidation state. At that time, oxidation state was not, the concept was not given. So oxidation state, or we call it OS, or oxidation number of the central metal atom. He at his time, it was called primary valency of the complex of the metal atom. Now we shall call it oxidation state of the central metal atom. The second one is called the secondary valency. The number of covalent linkages, number of ligand metal covalent connections or linkages Nowadays we call it, it is called the coordination number of the central metal atom. It is now called the coordination number. We shall write Cn of the central atom. Guys, if you are watching from outside, don't hesitate. If you will be continuing with me till the end of this program, picture abhi baki hai dost, picture shuru hua hai. This is introductory program. When you enter into hardcore discussion on metal ligand bonding, theories of metal ligand bonding, the stability of complexes. So many things will come up, interesting things will come up of the central metal atom. Now, let me give you an example and I will ask you to find out. You have to tell me two things. What is the primary valency in the language of Werner? What is the primary valency of cobalt? Now we will call the oxidation state of cobalt in the complex, and what is its secondary valency. Now we shall call what is the coordination number. How many linkages, how many single bonds, how many linkages are there? Secondary valency of cobalt. That is the coordination number of cobalt in the complex. Who can tell me? Yes, you can raise your hand. Those who are watching, quite a large number of guys are watching from outside. Congratulations for them, to them. So I would in the Sai. Yes,
Sir,
Sai.
oxidation state plus 3.
Plus 3 and coordination number.
Coordination number 6.
Is it okay, Krishna?
Yes, sir.
RS, are you there? RS? RS is not there. Okay. She will be watching later. Because this water, as we shall call it aqua, is a neutral complex, no charge. Cyanide is actually, you have written Cn, but it's actually Cn minus 1. So minus 1, there are 2. So minus 2. Ammonia is a neutral ligand. So charge 0. And chloride ion, which is outside the coordination sphere, is minus 1. So the sum of the negative charge is minus 3. The cobalt has to be plus 3. So you can find out the oxidation state of the metal atom in the complex from the formula, from the net charge of the complex ion, which I'll give. Had I not given this, the counter ion, chloride ion, simply I would have written plus 1. Here it is plus 1. The whole charge, the net charge of the complex ion is plus 1. So this is x minus 2. This is 0. This is 0. Is equal to plus 1. So x is equal to plus 3. So this is plus 3. And secondary valency, how many linkages? You know, there are all having only one donor atom. So 3 water means 3 plus cyanide, the carbon is the donor. So 2 plus ammonia, nitrogen is the donor. We shall study later on after some time. These are all monodentate ligands. One, two ligands. So one linkage for every molecule. There are 3 water molecules, 3 cyanide ion, 2 plus 1. So the number of covalent linkages, so you find 6. Undoubtedly, you will say the geometry is octahedral. That credit goes to Werner. He thought, can it be uh, trigonal prism? Can it be hexagonal? There are 2 alternatives to octahedral where the coordinate number can be 6. Can be hexagonal, it can be trigonal prismatic. But from the very analysis, you will find that for the tri, 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 uh, mm, triangular prism and hexagonal, there can be 3 geometrical isomers. But he only got 2 geometrical isomers. That is only possible if the geometry is octahedral, not prismatic. I mean, or it is hexagonal. I will discuss this thing in detail in our isomerism program, and that too stereoisomerism program. Nothing to worry. So here is what we are supposed to write down at home, which I have already told you. This is a neutral complex. There is nothing outside the coordination sphere. Here, this is the complex is cationic because anions are outside, swimming outside, and this is an anionic complex where the counter ion potassium ion is moving here and there. We have already done that. Lewis acid, Lewis-based concept. Cobalt 3 plus is sitting at the middle, and there are 4 ammonia sitting at the 4 corners of an octahedron, and 2 chloride ions are sitting at the 2 other places. If they are close to each other, then it is the cis form, cis symmetrical isomer. And what I have drawn here, I have copy pasted, is a cis one. If chloride ions will be remaining opposite, either this opposite or this opposite or this opposite, then they will have different properties that will be trans. We know not every complex will show isomerism, I mean stereoisomerism. So what are the conditions? How to remember them? I'll tell you the tricks how to remember them and all that later. Now, this we have already done. I was just wanting to tell you there are 3 types of complexes: neutral complex, like NiCO whole 4, only square bracket, there is no outside or after that or before that. So this is another example of neutral complex. Anionic complex, where potassium ferrocyanide ion has the ferrocyanide ion as the anionic complex. Similarly, tetramine copper, the real hero is the tetramine copper 2 plus. Sulfate ion is the counter ion, what we call spectator. You can also have 2 chloride ions in place of sulfate ion, carbonate ion in place of sulfate ion. So to make the valency equal, coordination number is 6. The only geometry, I can't say only geometry, there are other exceptional cases that have been also found out, but majority of the octahedral, majority of the compounds having coordination number 6 exhibits octahedral geometry. Tetrahedral geometry for coordination number 4, it is tetrahedral, or the alternative is square planar. That will come in a very big way in complexes. In normal covalent molecules, we have never come across with square planar geometry. But in complexes having coordination number 4, you will be getting more number of square planar geometry than tetrahedral geometry. And also trigonal, bipyramidal, all that we'll study. And it will have a fixed coordination number like 6 or 4 or 5 or 7, 6. And the oxidation state of the central atom is fixed. The example I have given you. And now for you to find out quickly for each one, this is the classwork that we shall do to find out the oxidation state, that is the primary valency as per Werner, and coordination number of the central metal in the complex, as it is called the secondary valency by Werner. So tell me, OS and CN. Quick.
2, 2 and 4.
Don't say 2. Werner told, because he was in 1913, he got Nobel Prize. Before that, he was working. In late 19th century, he was working, and he got the Nobel Prize in 1913, when perhaps your great grandfather was not born. Grandfather is of my age, almost my age, maybe little senior. Great. How much? Say, because since ammonia is a neutral ligand, no charge, and the whole net charge is +2, so x plus 0 is equal to +2, means the central metal atom also is in the +2 state. And what is the coordination number? Quick.
4
4
How many ligands are attached? 4. Tell me the second one.
plus
plus
3 and
3
6.
plus 3.
Because nitrite is an anionic ligand. Each nitrite has a -1 charge. So 6 minus 6. So x minus 6 and the net charge is -3. So x is equal to plus 3. So oxidation number of cobalt in this complex is plus 3. And it is really shameful for me to ask what is the coordination number. There are 6 is written, so 6. So in this case, what is the oxidation state? Copper.
plus
Plus
1.
1.
1
Oxidation state of copper
plus 1
plus 1, because x minus 4, because cyanide, each cyanide is -1. So -4 is equal to net charge is -3. So x is equal to plus 1. And coordination number I am writing on your behalf, 4. And what is the coordination, the oxidation state of molybdenum here?
0
0.
0
Because carbon monoxide is a neutral ligand, carbon monoxide. So if this is 0, this has to be 0. So this complex is a neutral complex, non-ionic complex. So the oxidation number, the oxidation state of molybdenum is 0 and coordination number as usual is 6. And tell me, this one is also a neutral complex. So what is the
plus
oxidation
3
state of
plus
Plus
cobalt?
3.
This is 0, this
plus
is
3
-2, this is -1. And since it is neutral, x -2 -1 is equal to 0. So x has to be equal to plus 3. So cobalt is in the plus 3 state. This is plus 1. This is plus 3. And what about the hexa aqua iron 2? This one.
plus
Plus
2
2 and 6.
Plus 2.
Yes, precisely. Water is a neutral ligand. So whatever is the net charge of the complex, same will be the oxidation state of the central metal atom plus 2. And coordination number as usual. What is the coordination number of the previous example? 1, 2, 1, 3
6.
6
plus 3. Again
6.
6. 3 water, 2 chloride ions, 1 cyanide ion. So the number of linkages will be 6. So it will be the coordination number is 6. And here it will be 6. And what will be the oxidation number of this? The last one, G.
plus 3
Plus
4
3.
Because this is
plus
x,
3
this is 0, this is plus -2. So x -2 is equal to plus 1, because the net charge of the complex is given plus 1. So therefore, the charge, the oxidation number of chromium is plus 3. This is plus 3 state. Now, a question arises, sometimes comes in the examination, why transition metal atoms form complexes most easily? Because they have high charge. Usually the charge starts from plus 2, plus 3, plus 4, plus 5. Therefore, small size. More is the plus charge, less is the size. And more is the polarizing power. And according to Fajan's rule, it has got more tendency to form covalent bond. And in this case, coordinate covalent bond. And other important reason that they have vacant d orbitals along with s and p orbitals vacant, because the metal ion is acting as a Lewis acid. It will simply make use of its vacant orbital, not use its electron. Vacant orbital to the ligands to form covalent bond, coordinate covalent bond or dative bonds. And of course, there are yes, the second point was they have vacant d orbitals along with s and p orbitals of appropriate energy to accept electrons from the ligands and form coordinate covalent bonds. Of course, some main group metals like aluminium 3 plus, stannic, plumbic, beryllium 2 plus, they also form complexes. Some of the examples I have given: aluminium, tin. Can you tell me what is the oxidation number of tin here? What is the primary valency as per Werner? This is
plus 2
tetrachlorido. Yes, because if this will be 2, there are 4 chloride ligands. So -4, the net charge will be -2. Similarly, you can find out, most important thing is that if there is no other ligand, you are putting a transition metal salts in simply water, it forms aqua complex. For example, Fe2 plus gives hexa aqua complex. The green solution that you call ferrosulfate solution is actually FeH2O whole 6 2 plus SO4 2 minus. It forms immediately coordinated to aqua water molecules and form a coordination complex ion. But once you put other strong ligands like cyanide ion, that they undergo displacement, the substitution reaction, just like in organic SN1, SN2. This substitution reaction occurs, the aqua ligands are substituted by more powerful ligands like cyanide ion, because that is a stronger ligand than aqua. We'll talk about that. And I am really excited because of this chapter is really very interesting and intriguing. So I have decided to make it a public program, so that others can benefit out of maybe my experience. Oh, yes, more than 40 years of my experience teaching this along with other topics. Werner's theory you have already done. Now you just write down, I forgot the color. It's not possible to memorize the colors. Now the first one is orange yellow color. You can write down just below the first compound. The second one was purple. The third one, the cis and trans. Cis was violet, trans was green. And the fifth one, we made it 3A and 3B, 4. Here in the table, I have made 3, 4, 5. In fact, they are different compounds. Maybe they are isomers, they are geometrical isomers, but still their colors are different, right? So this is green. This is also green. But see, the fifth category, non-ionic category, has the same color as the ionic category having one chloride ion outside. Colors are same, but look to the conductivity. It was giving nil conductivity. Nil conductivity, no ions, no silver chloride precipitate. But here it was having some conductivity, although the color is same, having 2 moles of silver chloride precipitated. So this is conductivity, I'm sorry. This is conductivity, and this is the number of moles. We had interchanged the column that we have written in our copies, but here the columns are opposite. Doesn't matter. More number of ions, total number of ions will be more, the number of silver chloride precipitated will be less. Okay. Now see here, this is an trans isomer. This is actually purple. Some people call it red. This is close to each other. The two chloride ions, they're close to each other. You can put in these two places, or these two places, these two places, or these two places. We'll talk about that in details in our isomerism program. But when they're opposite, these two or these two or these two, they will have transform, and the colors are different. This is green and this is purple. The green is the 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 transform is green, and the cis form is violet. Some people call it red also. It's very difficult to distinguish between the violet and red, the color that it exhibits. So in many literature you will find red, and in other literature you will find violet. I think violet is correct. Now subsequently, the last category, Werner could not. He could not find that. The possibility was 2, but he could not prepare. Subsequently, this 3,3 type, NH3 whole 3 and Cl3, the last category, there are also 2 different geometrical isomers that could be produced with different colors later on, right? And I have given you another set of data by the same famous Werner. Platinum plus 4 complexes with ammonia. 6 ammonia. And here the conductivity data I got from the literature. This is NH3 whole 6, Cl4, so total number of ions is 4 plus 1, 5. But the chloride ions are 4. So 4 moles of silver chloride precipitated, and the conductivity was maximum, 523 Simon centimeter square per mole inverse. And in this way, gradually it reduces until you have all chloride ion inside the coordination sphere, no conductivity, no silver chloride precipitate. This is another isomer analysis. I have already told you. Coordination number 6 category, you have cis and trans. We have already discussed. He also prepared the square planar complex of platinum 2 plus ET NH3 whole 2 Cl2. with coordination number 4, and that too square planar complex. We'll be knowing in details why this will be square planar, why not tetrahedral. Not tetrahedral. He prepared two totally different collars. I've not given here the collars. I will tell you in some other day, but they had different property, biological function. Cis isomer was famously called cisplatin, and it was at that time was treating cancer patients. They are acting as anti-carcinogenic substances. But trans was absolutely worthless. No anti-carcinogenic property. So the two different geometrical isomers were prepared by Werner, same square planar geometry, but different geometrical isomers. One, chlorine, chlorine, same side, chloride, chloride, same side, ammonia, ammonia, same side, but here chloride, chloride opposite, ammonia, ammonia opposite. Now, this we have discussed. There is ionic bond, there is covalent bond, there is a primary valency, secondary valency. Primary valency is non-directional. It produces ions, just like ionic bond. But that metal ion is not the ion. The whole elephant is the ion. But since it is losing electron, the ligands have not lost any electron. The metal ion has lost electron to the counter ions. That is why that is called the non-directional valency, and secondary valency is covalent. So covalent bonds are directional, hence secondary valency is directional. We have done all this, and now let us write down. I will for the coming few minutes, we shall be writing the different ligands. Before we close, denticity. Two things we will know. First is denticity, the number of donor atoms in a ligand. To if there is one donor atom, it is called monodentate or unidentate. Two bidentate. Two as if there are to bite the metal ion. Tridentate, three toothed. Tetradentate, four toothed. Pentadentate, hexadentate, and so on. Octadentate. So let us list, that is denticity. We'll talk about another term called hapticity. And haptic ligands are something very weird kind of ligands. We'll not talk about haptic bonds until we cover dentic ligands and the theories of metal ligand bonding. After that, I will talk about denticity and haptic uh, you know uh, ligands. Now let us talk about monodentate ligands. One donor atom. We can call one, two, 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 two. Instead of teeth, we will make a verb to do. So let us list one by one. The commonest is, the, let us make the formula, new name. Even I have found in many Western literature, in here, US also, many literature, they use old names. And short notation. Cl minus is chlorido. now the rule from 2015, the rule has changed. I will give you the reference for the learned audience who to refer. The original IUPAC rules changed in 2015, that for every type of ions, whether it is having suffix id, chloride, bromide, iodide, sulfide, or culminating in it, nitrite, sulfite, or at, nitrate, sulfate, carbonate, all, irrespective of caste and creed, you just replace E by O. This is the new rule. But previously, IDE was replaced by O, like chloro. Chloride was chloro, bromide was bromo, iodo, but now it is chlorido. Because I will tell you the latest. But old is gold, dishonor the old, chloro was the old, but I will chlorido. This there is no short notation. Then bromido, bromo, iodido, iodo. The old name was iodo, iodido. Chlorido, chloro, cyanido. It it sounds little weird to you, but it is a fact. I will share that paper to you. Cyanido. Now it was called cyano. In many books, you will still find cyano. Latest books, printed books, you will find cyan, but it is actually. And these are all anionic ligands and monodentate. Hydroxido, sounding weird, it was called hydroxo. Now tell me what, I don't know what was the previous name. It is hydrido. Can you call it hydro? Hydro will sound weird. Hydride, E replaced by O, hydrido. I don't know what is this. Hydro, I can't write hydro. Might be there is an exception, hydrido minus. And you leave a little bit space. There will be many more joining in the fray, in the competition. We have some ligands. We write NC minus. It is called isocyanide, where nitrogen the cyano is carbon donor. I will tell you the other classification. These are called ambidentate ligands. Same formula, but donor atoms are different. At one time, only one atom can donate, so they will act as monodentate ligands. Although there are two alternative donor atoms, both cannot work together, only one. So isocyanide, but they were calling isocyano. Similarly, OCN minus, where O is the donor, it is cyanato. This is nothing. That was the previous and new same. Cyanato. And NCO, where N is the donor, it is isocyanato. Same. AT, IT, same. But IDE, the whole IDE was replaced by O, but now only E, like others, E is replaced by O, and so on, leave a space. Then we go for neutral. Same monodentate neutral. H2O is called aqua. Previously it was called aqua. Ammonia, it is called amine, double M. Remember, that is the IUPAC recommendation for inorganic. There is a difference. Amine. Carbon monoxide is called carbonyl. Nitrogen monoxide is called nitrosyl. Cationic ligands are very, very uncommon. NO plus, nitrosonium, or sometimes called nitrocilium. Cl plus, chloronium. These ligands are very uncommon, but still will come across. Leave a space for monodentate, then go for bidentate. Two theta antotaro. Two teeth to bite. And from these onwards, they are all commonly called polydentate ligands. More than one donor. More than one donor atom, bidentate, tridentate, tetradentate, all are commonly called polydentate ligands. And let us start from the neutral ligands. The most widely used bidentate ligand is ethylene diamine. Don't worry, I will never forget that I'm dealing with the beginners. Maybe you are in class 12, but beginners. So I will start from the very rudimentary till depth. So ethylene diamine, no space. And here there is one M. And the short notation is En. I am not giving in tabular form, very time consuming. Ethylene diamine is En. Short notation is En. Nobody writes ethylene diamine in writing the formula. Everyone write En. Because here, supposing, metal ion having its charge N plus will be coordinated here. So one ethylene diamine molecule will have two teeth to bite. So two tooth. And if there will be two such ethylene diamine, then coordination number 4 is satisfied. If there are three such ethylene diamine, then 2 plus 2 plus 2. The coordination number 6 is satisfied, but they will be sitting in such a manner that the geometry will be looking like an octahedron. We'll talk about that later. Then we have propylene diamine. This is propylene diamine, PN. We have oxalato. These are the two teeth, O minus, O minus. This is C2O4, 2 minus, but it is famously called OX2 minus. The short notation is OX, small o, small x, 2 minus. OX means oxalato, C2O4. And we have another glycinato. These are anionic. I will not write whether it is neutral or these are neutral. Propylene diamine is neutral. Then you have carbonato. Oh, sorry. Let us complete glycinato. Just now you have finished the amino acids. So if you have one O minus in the ionic form, you know at what pH this remains in the anionic form. I can remind you that remains in higher pH. So the H plus ion is removed from NH3 plus the deuterion and it remains in the anionic form. So this CH2 NH2. So this is one tooth, the other tooth is here. Here you will be the metal ion satisfying coordination number of 2 from one glycine, and that is called glycinato. So TO will glycinate, will be called glycinato. E will be replaced by O, glycinato. And it will be shortly called GLY1 minus. It is an anionic ligand, remember, because in charge calculation, when you find the oxidation number, if it goes wrong, then the entire multiple choice will go wrong. The most important is to find the oxidation state of the central metal atom. For that, you must know the ligands. What is the charge of the ligand? Glycinato. Then you have carbonato. This is a very CO3 2 minus. This is a very simple ligand. Carbonato, carbonate, carbonato, sulfato. Let us write pH. British English is pH. SO4 2 minus. Same. Of course, there are two sulfate ion, two double bond O. They will not donate. So these two will donate. Donors. So sulfato. And the another interesting bidentate ligand is, oh, monodentate ligand, I forgot, is pyridine. Neutral ligand pyridine is a very fantastic. Simply it is called pyridine. It has got a nickname PY. You have ACAC, acetyl acetonato. ACAC, AC, 1 minus. I'll tell you how it will be looking like. This is the enolate form of acetyl acetonato. So this is 1, this is -1. Remember, that should be 1. So this is a very important ACAC, acetyl acetonato, having a net charge of -1. Similarly, you have BAC, benzoyl acetonato. No gap. So in place of acetyl, you have a benzoyl, pH, C6H5. This is BAC, -1. DMZ H-1, dimethyl glyxamato. Not Zomato, the house that supplies food in the late hours of evening, night 11 o'clock, you order to Zomato, or what is the other food delivery, online delivery company? Can you tell me? Zomato, and other one is Swiggy. It is dimethyl glyoxine mato, and it is the I will just ask you to draw the structure from here to save time. You see, I have listed so many, and you also write down those which you have not written, like oxido, O2 minus, monodentate. We have so many things in my table, which I will share with you. Also in the description box in the video, I will be giving you this file for you to use, to download the file and use. I've given so many acetato, nitrato. If nitrogen is the donor, then it is nitrito N. Previously, it was called nitro. If oxygen is the donor, formula is same. It was written as ONO, but same formula. Formula is same. Oh my God. Okay. It was called nitrito, but now it is called nitrito O, and this is nitrito N, written as NO2 minus. This is ONO minus. CN minus is cyanido. They were calling cyano. Still they are calling cyano. They have to be little hero marka. This instructor is a bit hero marka. I'm sorry for this self proclamation. Because why I'm saying, because if you do not tell you the recent developments, then you are a past person, a ghost. I'm sorry. This is isocyanide, isocyano. This is acetato. This is thiocyanato, sulfur donor, and this is isothiocyanato. This is something has happened. Yes, I have to. Oh, yes. Okay. Now it's okay. Oxido. Now it is called oxido. It was called oxo. But what about hydrido? There is no name for hydrido. Cannot call hydro. But for AT and IT, no rule is different. Same. Only O was replacing E, azido. And then in neutral type, we have dioxygen, dinitrogen, neutral type, triphenyl phosphine, you write down, nitrosyl we have done, pyridine, then methylamine, dimethylamine, trimethylamine, trimethyl phosphine, and this we have done. Bidentate ethylene diamine, dipyridine. This is called bipyridine, bipyridine. This is phenanthroline, phen, neutral. This is propylene diamine, PN, neutral. This is little bit hi-fi, 2 dash bis diphenyl phosphino 1 dash binapthyl, binap. This is DPPE. This is 1 bis diphenyl phosphinoethane. These are all unusual, not very much in use. Urea, thiourea, these are all bidentate ligands. Oxalato, glycinato, carbonato, acac. I have told you this is acac, this is BAC, benzoyl acetonato, right? And this is dimethyl glycosimato. You can draw the structure now. It is a dioxime of the alpha diketone, butane 2,3-dione. It is a dioxime of alpha diketone, butane 2,3-dione, and one proton has been removed by alkyl treatment. One O minus is there and one OH is there. Therefore, I have written DMZH. If you take all the proton out, then it will be DMG2 minus. But usually we write DMGH1 minus. Sometimes H is not written, फिर भी they take -1 as the charge. Be careful. DMG is taken as -1 charge. It should write DMGH because only one, the oxime, it is a dioxime. You have already studied aldehydes and ketones chapter. The carbonyl group reacts with hydroxylamine to form oxime. So diketo, dioxime, but one proton is lost. So nitrogen atoms are the donors, not oxygen atoms. So I have written. And sulfato, thiosulfato. Then we'll go for a tridentate ligand. We will be tomorrow, we shall be naming them. So today I told you this is a 1 hour, maximum 1 hour, 15 minutes. We have already 18 minutes past 1 hour. So we'll be only today acquainting ourselves with, then let us go for tridentate, one each. Important. Tridentate ligand, they are very uncommon. Three-tooth, tooth is, it is, interesting. This is diethylene triamine. Diethylene triamine. Put a single M. There is one lone pair here, and this is secondary amino, and these two are primary amino, and the metal ion will be sitting somewhere in the middle. M stands for any metal, may it be transition or any metal, and with its charge oxidation state N plus. So this is one nitrogen and this is one other nitrogen. There are 3 nitrogen donors, diethylene triamine, and it is called di-en. This short notation is di-en. And in tetradentate type, tetradentate, then it is triethylene tetramine. Tetra, I mean, there are 2A. When one diethylene triamine will satisfy a coordination number of 3. Two such di-en will purely quench the hunger. The coordination number 6 will be attained by only two free-toothed ligand called di-en, diethylene triamine. Tetradentate ligand is triethylene tetramine. So there are two secondary amino and two primary amino. In between, there will be two secondary amino. So one here, one here, one here, one here. And the metal ion will be somewhere sitting at the middle to coordinate with it. And one of them, and one ligand having 4 tip will satisfy a secondary valency or coordination number of 4. And another two monodentate ligand will make the the coordination number of 6. The octahedral geometry will be automatically coming out. If it is coordination number of 6, whether it is by 3 bidentate ligands or one tridentate ligand with 3 monodentate ligands or 2 tridentate ligands or one tetradentate ligand and 2 monodentate ligands or one tetradentate ligand with a bidentate ligand, they will be arranging in such a way that the geometry will be octahedral. Similarly, this is pentadentate. Just you extend this, will be tetraethylene pentamine. Tetraethylene pentamine. This is tri-en. This is tetraen. I am not drawing the structure. There will be two primary amino groups and the two terminals, and there will be three secondary amino groups: CS2, CS2, NH, CS2, CS2, NH, CS2, CS2, NH, then CS2, CS2, NH. So just writing this, and it's here you will find tetradentate ligand. There are many other which are not important at all. Silane is not at all required for you. And pentadentate tripolyphosphate P3O5 5 minus, but actually it acts as a tridentate ligand. Two teeth remain unused. So although there are 5 teeth, but only it acts as a tridentate ligand or sometimes bidentate ligand. The example I have given you with a metal ion, only 3 are being used and other 2 are simply staring. And the other one is steppa. So I was missing out the nickname. This is tri-en. Tri-en is okay, but I was missing the nickname of tetraethylene pentamine is steppa. And so the last but not the least is the hexadentate ligand. Hexadentate ligand is EDTA, which is very much used in inorganic chemistry and reactions. Purify to remove hardness, calcium and magnesium, and they form very easily EDTA complex. EDTA is ethylene diamine tetraacetato acetic acid, and the ions they have been ionized by adding alkali tetraacetato. So it's like this. You first draw the structure of ethylene diamine NH2 NH2. So instead of NH2 NH2, it will be CS2CO minus, CS2CO minus, CS2CO minus, CS2CO minus. So this is acetato, 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 tetraacetato. And therefore, if metal ion is somewhere sandwiched in the middle, so one nitrogen donor here, one nitrogen donor here, and all are oxygen donors here and here. I'm drawing in a curved manner. because I can't draw an ideal geometry to show you an octahedral geometry, but I've given you how octahedral geometry can be visualized by drawing that this is EDTA, EDTA, and remember, either you can write in small letter that has to be 4 minus, remember, it is EDTA 4 minus. But if one of them will be neutral, it can be EDTA H3 minus. One of them is in the COOH form, it will not ligand, it will not coordinate, it will remain as such. Only 5 donor atoms will be active, the other atom will be inactive. So such ligands are called flexidentate ligand. I have 6 teeth, but I am using in some complex 5 teeth, in some complex all the 6 teeth, some complex 4 teeth. So different number of tooths, teeth are used in different complexes, then such ligands are called flexidentate ligands. So EDTA and its hydrogenated counterparts are called flexidentate ligands, and this is sometimes it uses only 4 donors, so that 2 will remain in the neutral form EDTAH2. This will be 2 minus. So it will be coordination number. This will be 6. Cn is equal to 6. This Cn is equal to 5. This Cn is equal to 4. So these are called, I will be naming them tomorrow, flexidentate ligand, just like I told you that cyanido, isocianido, or they call cyano, isociano, they are called ambidentate ligand. They have 2 alternative donor atoms, but one atom can be used as donor at a time, not both. But here, flexidentate, they have multiple donors, but in some complex, it will use all of them, some less than that, in others still less than that. So different number of donor atoms will be used in different complexes. In that case, they are called flexidentate. We'll talk about that later. So आगे आगे देखिए होता है क्या. So I have given you, today I had a plan to complete nomenclature. That is not a big deal at all. It will take only 15-20 minutes, and we'll be making a lot of practice in the class. That will consume some time. All varieties of complexes, which I'll write the IUPAC name in our coming tomorrow's class, and then we'll go for isomerism. Tomorrow we shall start structural isomerism, no doubt. Now see, I have given many more. This is the octahedral representation of the structure. Metal ion is sitting at the center, where this NCH2CO minus, this O minus is at the top, this NCH2CO minus at the bottom, and this O minus, N, they are lying in the 4 corners of a square. So if you join this, it will be an octahedron. But just for a fun sake, you can write down this CH2, CH2N, but it doesn't really work like this. It has to orient itself in octahedral manner, so that the geometry has to be octahedral, EDTA 4 minus. Similarly, there will be octadentate ligand, 8 tooth do. It will be DTPA 5 minus, diethylene triamine pentaacetato, just like diene, diethylene triamine. Similarly, this is diethylene triamine CH2, CH2, NH2. Then then CH2, CH2, NH2, CO, and there will be CH2, CH2. What will be another N? Oh, N, and yeah, CS2, CS2 written in this is, coordination number is 8. This is cubic structure. So N, CS2 CO minus, CS2 CO minus, then CS2 CS2, N, CS2 CO minus, CS2 CO minus. This is one CS2 CO minus. This is the other CS2 CO minus. What is the other CS2 CO minus? N. No, this is N. This is to N. So CS2CO minus here, CS2CO minus here, 2 CS2CO minus, and here 2 CS2CO minus. So this will be, and here, there are, this is a secondary. Oh, there is a secondary amino. This is NH. So there will be only one CH2CO minus. So 2 plus 2 plus 1. So 5 CH2CO minus. That is why it is pentastato. The middle one is a secondary amino. So there is only CH2CO minus. But the terminal NH2, NH2, there will be 2 CH2CO minus, 2 CH2CO minus. And it will be DTPA 5 minutes. And we'll talk about microcyclic ligand, chelatic ligands tomorrow. So we close today's session. I'm sorry that we have already covered 1.5 hours class. I was little optimistic and little more ambitious to finish the nomenclature part, but tomorrow we shall make some revision, and at the same time at 5 o'clock, guys who are watching from directly from the YouTube or now watching at a later time, find it interesting and you will benefit. Don't hesitate to hit the like button. Don't be greedy to remain silent. Hit the like button, and also if not subscribed, subscribe to my channel. Bye, see you tomorrow.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Hello, Ruoma, tamo sa tigo,